A matrix difference equation is a difference equation in which the value of a vector of variables at one point in time is related to its own value at one or more previous points in time. Using matrices, occasionally, the time-varying entity may itself be a matrix instead of a vector. The order of the equation is the maximum time gap between any two indicated values of the variable vector. For example, is an example of a second-order matrix difference equation, in which X is an n times 1 vector of variables and A and B are n times n matrices. This equation is homogeneous because there is no vector constant term added to the end of the equation. The same equation might also be written as or as. The most commonly encountered matrix difference equations are first-order, non-homogeneous first-order matrix difference equations and the steady state. An example of a non-homogeneous first-order matrix difference equation is with additive constant vector b. The steady state of this system is a value x** of the vector x which, if reached, would not be deviated from subsequently. X** is found by setting in the difference equation and solving for x** to obtain where is the n times n identity matrix, and where it is assumed that is invertible. Then the non-homogeneous equation can be rewritten in homogeneous form in terms of deviations from the steady state. Stability of the first-order case. The first-order matrix difference equation xt x** equals a xt1 x** is stable, that is, converges asymptotically to the steady state x** if and only if all eigenvalues of the transition matrix A have an absolute value which is less than 1. Solution of the first-order case. Assume that the equation has been put in the homogeneous form. Then we can iterate and substitute repeatedly from the initial condition, which is the initial value of the vector y and which must be known in order to find the solution, and so forth. Assume A is diagonalizable. By induction, we obtain the solution in terms of T, where P is an n times n matrix whose columns are the eigenvectors of A, and D is an n times n diagonal matrix whose diagonal elements are the eigenvalues of A. This solution motivates the above stability result. Shrinks to the zero matrix over time if and only if the eigenvalues of A are all less than unity in absolute value. Extracting the dynamics of a single scalar variable from a first-order matrix system. Starting from the n-dimensional system, we can extract the dynamics of one of the state variables. Say the above solution equation for shows that the solution for is in terms of the n eigenvalues of A. Therefore the equation describing the evolution of by itself must have a solution involving those same eigenvalues. This description intuitively motivates the equation of evolution of which is where the parameters are from the characteristic equation of the matrix A. Thus each individual scalar variable of an n-dimensional first-order linear system evolves according to a univariate nth degree difference equation, which has the same stability property as does the matrix difference equation. Solution instability of higher-order cases. Matrix difference equations of higher order, that is, with a time lag longer than 1 period, can be solved, and their stability analyzed, by converting them into first-order form using a block matrix. For example, suppose we have the second-order equation with the variable vector x being n times 1 and A and B being n times n. This can be stacked in the form where is the n times n identity matrix and 0 is the n times n 0 matrix, then denoting the two n times 1 stacked vector of current and once lagged variables as in the 2n times 2n block matrix as L. We have as before the solution also as before. This stacked equation and thus the original second-order equation are stable if and only if all eigenvalues of the matrix L are smaller than unity in absolute value. Nonlinear matrix difference equations. Riccati equations. In linear quadratic Gaussian control, there arises a nonlinear matrix equation for the evolution backwards through time of a current in future cost matrix, denoted below as H. This equation is called the discrete dynamic Riccati equation, and it arises when a variable vector evolving according to a linear matrix difference equation is to be controlled by manipulating an exogenous vector in order to optimize a quadratic cost function. This Riccati equation assumes the following form or a similar form, where h, k, and a are n times n, c is n times k, r is k times k, n is the number of elements in the vector to be controlled, and k is the number of elements in the control vector. The parameter matrices A and C are from the linear equation, and the parameter matrices K and R are from the quadratic cost function. See here for details. In general, this equation cannot be solved analytically for in terms of t, rather, the sequence of values for is found by iterating the Riccati equation. However, it was shown in that this Riccati equation can be solved analytically if R is the zero matrix and n equals k plus 1, by reducing it to a scalar rational difference equation. Moreover, for any k and n, if the transition matrix A is non-singular, then the Riccati equation can be solved analytically in terms of the eigenvalues of a matrix, although these may need to be found numerically. In most contexts, the evolution of H backwards through time is stable, meaning that H converges to a particular fixed matrix H*, which may be irrational even if all the other matrices are rational. See also stochastic control #discrete time. A related Riccati equation is in which the matrices X, A, B, C, and E are all n times n. This equation can be solved explicitly. Suppose, which certainly holds for t equals 0 with n0 equals x0 and with d0 equal to the identity matrix. Then using this in the difference equation yields so by induction the form holds for all t.